Thank you for coming. The talk today is Durable Execution, the essential abstraction for reliable platforms. And I'm going to jump right into it, just dive into it with a quick demo that's going to provide the context for everything else that I'm going to cover during this session. So I'll open up my terminal window, and I think it's easiest to understand durable execution when you look at what normal execution is. When you don't have durable execution, it's something that's easy to compare, but maybe hard to understand on its own. So I'm going to show you a program that I've written in Python, just a simple program here. And the business logic is I've defined a function that's going to count from 1 to 10. So I've got a function that takes a parameter that's a limit. It's going to assign a number, a variable called number. It's going to assign it the value of 1. And then it's going to iterate over, or it's going to use a while loop to count up to that limit. And while that number is lower than the limit, it's going to enter the loop. It'll print out the number. It'll increment the number by 1, and then it's going to sleep for 1 second. So here on lines 9 through 14, that's where the function is defined. And we also need some code to call that function. So I've got another simple program here that just imports the function count2, and then it's going to count to and pass the number 10. So as you might guess, what's going to happen when I run this is going to print 1, 2, 3, 4, 5, and I'm going to kill it right there. I'm just going to stop that program. Even though it's supposed to count up to 10, I terminated it before it reached that goal. Unexpected terminations like this happen all the time for a variety of reasons. It could be software defects, it could be power outages, hardware failures. I'm sure you've experienced these things many times before. I'm going to restart it now, but before I do, I want you to guess. Just think to yourself, what number is it going to display when I start it up again? It left off with 5, so what number is it going to show now? It starts over with 1. I bet most of you guessed this right. Even though the last number was 5, when I run it again after a crash, it starts over with 1. Of course, you know the answer because you understand how computers work. You've probably written applications, you've seen them crash, and you've had to deal with the consequences. But I bet if you ask this same question to someone who's never written a line of code, they'll answer that the next number would be 6. Why? Well, it's because they don't know how computers actually work. What they're telling you is how they should work. And now I'm going to show you that they actually can work like that. So I'm going to switch directories and go to durable execution, and I'm going to run a program to start counting. And just like before, when it reaches 5, I'm going to kill it. But unlike before, where it started over with 1 because it lost the state of the application, it lost the notion of progress, this one starts over. This one continues on as if that termination never even happened. So the ability to overcome a crash and continue making progress, it's not only possible, it's what many thousands of organizations around the world rely on to make their software more reliable and their developers more productive. What I'm talking about is called durable execution. And now that you've seen it in action, I'm going to explain more about what it is and how it works. So let's get started. Let's start at the beginning and explore the role of execution. As developers, we spend a lot of time thinking about code. In the end, it's just a set of instructions that describe the steps that you use to achieve some goal. To make an analogy, it's like sheet music. The music that you see here, it's not a concert. It doesn't make a sound. You're only going to hear what the composer intended when the musicians pick up their instruments and execute those instructions. The same is true for code. It doesn't matter whether I write the code down with pen and paper or put it into a computer. It's just a set of instructions, and it doesn't do anything by itself. Achieving the goal requires execution. Execution is what brings the code to life. I'm going to show you a basic program in Python, but I don't want you to worry if you're not a Python developer. I'm going to walk it through line by line. This program counts using letters of the alphabet rather than numbers like I did before. So here's what happens when we execute the code. The operating system creates a process and assigns it an ID that distinguishes it from all the other processes running on that machine. And because the operating system controls the underlying hardware, it allocates the resources that are required for execution, like memory and processor time. I'm now going to step through the code as it runs. The very first line is a comment. Since it begins with a pound sign, the computer ignores it. That line is meant for humans, not computers. The next line, which I've highlighted here, defines a variable called letters and assigns it a value, which is a string made up of each letter in the alphabet. The next two blocks of code define a couple of functions. The computer skips over those for now, since neither will do anything until something calls it. Execution continues with the last line in the program, which calls the count with letters function, passing it a value of 5. Let's look at how that works step by step. It now enters that function, which is going to output a sequence of 5 letters, A, B, C, D, and E. It declares a variable to keep track of the count, assigning an initial value of 0. The laptop screen on the right is going to show the current value as I step through the code. Now it hits a while loop, evaluating an expression that determines whether we've counted to 5 yet. Since the counter is 0, it enters the loop. Here's another function call. This one passes the current count as a parameter and assigns the result to a variable. The function just retrieves the letter corresponding to that number. And it does so using that number as an index within the string of letters defined at the top. In this case, the value is 0, so it's going to return the first letter, which is A. Control now returns to the original function, which prints that letter to the screen, and then increments the counter. Since the counter value is less than 5, it enters the loop again, and it calls the other function again, and it returns another letter, B, which the program now displays. After incrementing the counter again, it now has the value of 2, so we'll do another iteration. Uh-oh, maybe we won't. Something has gone wrong here. The process terminated, which means that this execution has unexpectedly come to an end. What happened? Well, there's a lot of different possibilities. It could be that the application crashed. For example, there could be a bug in the application code, such as trying to divide by 0 or accessing an array using an invalid index number. It could be a bug not in our application code, but a bug in a library that we're using, or maybe the Python interpreter. The process could also terminate if the operating system crashed. That could be caused by a bug in the kernel. Maybe someone applied a patch at just the wrong time, and that caused the machine to reboot before execution completed. It could be that the machine shut down because it lost power. Perhaps a fan inside the computer stopped working, causing the processor to overheat, and now we've got a hardware failure on our hands. Regardless of the reason, the outcome is the same. We've lost the value of all the variables that were updated as the program ran. Also, the program counter was reset when the process exited, so we no longer know which statements already ran nor which one should come next. And so begins the transformation that everyone experiences when learning to code. The joy of seeing your program run is replaced with the pain of watching it fail. It's a paradox. Execution is what brought the code to life, but it also introduced the possibility of failure. Late-night pages, production problems, and post-mortem reports all change how engineers see the world. As we gain more experience, we try to learn from each incident. And as time goes on, we get better at anticipating nearly everything that might go wrong. And we begin to design applications defensively. You'll see evidence of this in the code base for any serious application. The so-called happy path, where everything goes according to plan and you achieve your goal, is completely overshadowed by the effort involved with anticipating and trying to handle everything that might possibly go wrong along the way. Today's applications are distributed systems, so there's many more potential points of failure. Services stop responding, networks go down, servers lose power, hardware fails. As developers, we have to deal with all of it. The goal of our application becomes obscured by try-catch blocks and complex error handling. The code takes a long time to write, and it becomes a nightmare to try and maintain. Although we may see ourselves as realists, our friends and family may see us as pessimists. That's because we wear the scars of surprise edge cases, production problems, and all of the complexity it takes to build reliable applications in a fundamentally unreliable world. Fortunately, an alternate reality with a much brighter picture awaits us. Durable execution. I demonstrated durable execution earlier, and now I want to define it. Durable execution is crash-proof execution. That definition is memorable, it's easy to understand, and it's a good way of looking at it. Describing something as crash-proof doesn't mean that a crash isn't possible, it means that a crash has no consequence. To make an analogy, I have a watch and it's waterproof. It doesn't prevent me from falling into a pool, but if that happens, my watch is guaranteed to continue working. Durable execution is made possible by an abstraction that insulates code from failures, enabling applications to continue running despite them. This abstraction is provided by a system known as a durable execution platform. Temporal is one such platform, but it's not the only one. Most of these platforms, including Temporal, refer to this abstraction as a workflow. The term workflow can mean different things to different people. In some cases, it can evoke unpleasant memories of having to define your business logic using diagrams or a markup language like YAML or JSON. Well, in Temporal, workflows are defined with code, so you can leave those unpleasant memories in the past. When you hear the term workflow with Temporal, you can interpret it as a function or method with durable execution. Once a Temporal workflow starts running, it will guaranteed to be continued no matter what. To understand what durable execution is, it's helpful to see what things look like without it. I'm going to revisit that earlier example, but instead of stepping through the code again, I'll use some graphics to illustrate how it's affected by a crash. Here's the computer where it runs. Its operating system creates a process and outputs the first in a sequence of 5 letters, followed by the second. And now, for whatever reason, it crashed. Unfortunately, the execution came to an end when the process terminated. The underlying problem here is that normal execution is bound to a single process running on a single machine. Durable execution virtualizes this so that execution can take place across a series of processes, each of which could potentially run on a different machine than the one before. That means that durable execution provides fault tolerance for crashes, regardless of whether the root cause was hardware failure or software failure. Let's see what it would look like with durable execution. A new process starts up and execution begins within it, just like before. Here's the first letter in the sequence, and now the next one. It crashes at the same point as before. The process is terminated, but since we have durable execution, this is not the end of the story. Durable execution guarantees that it's going to continue with what comes next. It does this by enabling execution to resume in a new process. The application state will be unchanged. The value of the variables in the code will be equal to what they were at the time of the crash. And the code will continue running right from where it left off. Let's say the execution makes it one step further and then crashes again. This time, let's say that the process terminated because of hardware failure. In this case, the execution will continue in a new process on a different machine. Once again, the application state is unchanged, and execution continues with the next step. At this point, the code has finally achieved its goal, and execution is now complete. To summarize what happened, execution began in process number 1, continued in process number 2, and completed in process number 3. Here's the takeaway. Execution might be tied to a single process on a single machine, but by virtualizing it, durable execution allows incremental progress across a series of processes. Durable execution is the bridge that ties them together. And because those processes can span multiple machines over time, durable execution enables an application to overcome crashes, regardless of whether they were caused by software or hardware failures. With durable execution, the physical representation of what took place is below the line. It's true that this execution spanned 3 different processes across 2 different machines, but practically speaking, it doesn't matter. It doesn't matter because the developer experiences the logical representation, where these crashes had no consequence. It's as if they never even happened. And that changes fundamentally the way that you approach the practice of software development. Okay, now I'll explain how Temporal achieves durable execution. When people first learn about durable execution, and this was the case for me, often the first inclination is to assume that it's taking snapshots of memory. Although that would be one way to do it, in practice, it's not a very good approach. One reason is that it would have poor performance. Another would be that workflows can run for months or weeks or even years, and during that time, your business is going to change. Your needs will change, and your code needs to evolve along with it. But with that approach, modifying the code would invalidate the snapshot. The way that Temporal and most other durable execution platforms do it is by using a technique called history replay. As you'll see, this is actually a really elegant approach. When I first learned about it, my immediate thought was, why didn't I think of that? I'll begin my explanation with a quick overview of Temporal's architecture. As you've learned, workflows are the core abstraction in Temporal. They're functions or methods that define the sequence of steps for your business logic, and they have the benefit of durable execution. If a crash occurs during workflow execution, its state is automatically reconstructed and execution will then continue as if that crash never even happened. So let's look at an example. Since I'm explaining the concept, I'll use diagrams to illustrate it since that won't require you to understand any particular programming language. You could implement this workflow in any language supported by a Temporal SDK, such as Python, Java, TypeScript, PHP, Go, C#, or Ruby. The use case here is that we're processing orders for a pizza shop. The input for this workflow contains details about the order, such as the customer's name and delivery address, the list of pizzas that they want, and their credit card information. When the order is received, it first iterates over the list of pizzas, adding up the price of each one to determine the total cost. Next, it calls a microservice to determine how far away the delivery is from the shop. If it's outside the range, the order can be canceled. Next, it checks to see whether the total price is over $50 because we're having a special. And if it is over $50, we apply a 10% discount. Finally, it charges the customer's credit card for the order and then returns a confirmation number as output. Two of these four steps are internal to the workflow. They don't rely on and cannot change the state of other systems. They are deterministic, which means that every single time we invoke them with a given input, we will get exactly the same result. In this case, these steps just do some arithmetic. If you have an order for 5 pizzas at $12 each, the first step is always going to produce $60 as the output. The third step, which evaluates the price and conditionally applies a discount, will also produce the same result every time. If the order total from step 1 is $60, then it's going to apply the 10% discount, resulting in a final price of $54. However, the other two functions are non-deterministic, meaning that they could behave differently from one invocation to the next. These are error-prone operations, which, unlike the other two steps, introduce the possibility of failure. The service that returns the distance to the delivery address might be offline, for example, or the network might be down. Likewise, the payment service used to charge the customer may be under heavy load or returning error messages in response to our requests at a given time. Achieving durable execution through history replay requires that the workflow code must be deterministic. That means that 2 of the 4 steps aren't allowed in the workflow code. This raises the question, if the workflow code must be deterministic, how can we call the 2 services that we have to call to process the order? Let me introduce another part of Temporal's application architecture, which provides the solution. Since we can't include non-deterministic code in the workflow, we move it into separate functions or methods, which are known as activities. An activity does not have to be deterministic, and because it's used for error-prone operations, such as calling a service or querying a database or doing file I/O, it's automatically retried if it does fail. Here's what it looks like when we put the code to call the distance and payment service into activities. The code goes into its own function, one for calling the distance service and another for charging the customer. We then reference those in the workflow, so as the workflow runs, those activities get called. Just like the workflow itself, those activities can accept input and return output, and the workflow can make decisions based on the output. For example, canceling the order if the customer lives too far away from the pizza shop. This brings me to the next part of Temporal's architecture, the worker. The worker is responsible for running the workflow and activity code. The implementation of a worker is provided by a language-specific library known as a Temporal SDK, so you don't have to develop it yourself. You just need to configure, create, and start the worker. You need at least one of them running for your application to make progress, but it's common to run many of them, perhaps dozens or even hundreds of them, typically spread across multiple machines. This increases the throughput and availability of the application. The final piece of the architecture is the temporal service. This is a back-end system that manages workflow executions. But I want to be clear that it does not execute the workflow and activity code. The worker does that. The temporal service is something you can self-host by running it on your own machines, or you can use our temporal cloud service, in which case our expert staff monitors and manages its operations so you don't have to. Here's what the temporal service does. When a request to execute a workflow comes in, the temporal service creates a task which provides details of the execution, and it puts it into a task queue that the workers monitor for a given type of workflow. When a worker has spare processing capacity, it's going to pull the task queue, find the task, execute the code, and then report the result back to the temporal service. At every step along the way, the temporal service updates its record of what's taking place for that workflow execution. That record is known as the event history, and it's this information that allows a worker to reconstruct the application state following a crash. Let me walk you through it. I also want to point out that the temporal service is external to the application. It's typically running on a different machine and could even be in a different data center than the application itself. For this example, assume that the workflow execution is already underway. To keep this brief, I'll omit the parts about the workflow execution starting. The interesting part here is about the activity, but I'll put it all together for you in the end. We're getting ready to begin the second step, which calls the microservice to determine the distance to the customer's address. The temporal service has created a task that says which activity to execute and also includes the customer's address to pass in as input to the function. The temporal service adds a record to the event history to reflect the fact that it's created this task. When the worker pulls the task queue, it sees the task and then removes it from the queue. The temporal service adds an activity task started record to the event history, which signifies that a worker has accepted the task. The worker now executes the get distance activity, which calls the microservice to get the distance to the customer's delivery address. When it's complete, the worker reports the result to the temporal service, which then adds a new event called activity task completed to the history. This not only documents that the activity completed successfully, but it also documents the result that it produced. At this point, you have all the pieces needed to understand what happens if an application crashes. Let's say that the worker that had been handling this execution crashed. When the temporal service doesn't get an update from the worker after some period of time, by default it's 10 seconds, although it's configurable, it's assumed to have crashed. So the worker puts tasks into the task queue for another worker to pick up. It first asks the other worker, that is, was this activity execution requested during the previous run? If the answer is yes, then it continues on. And that's the case here. The history reveals that the answer is yes, this activity was requested during the previous run. Next, it asks, did the execution actually begin? Once again, the history shows that it did. Finally, it wants to know whether the execution completed, and if so, what the result was. The history shows that the activity did complete and that it returned a result of 15 kilometers. That is stored in the event history. So instead of running the activity again, it assigns the result from the previous execution. The worker will continue this process until it reaches an activity that did not complete during the previous run, in which case it will execute the activity as it normally would and then update the event history with all of the details. By the way, if you want to see this in much greater detail, I recommend our Temporal 102 course, which will go through this code line by line and show what's actually happening behind the scenes. And that takes me to the end of my explanation of durable execution. Thank you very much for your time and attention, and I'll look forward to your questions.
Okay, we do have one question, and then I will launch the second poll. Mandar is asking how to pass sensitive information to the worker, such as user token.
That's a great question. When people learn about temporal and they see the event history, and they then, as I explained here, you have information, the result of every execution, activity execution, the workflow execution, as well as the input that is passed to each activity and workflow execution. All of that information is being stored in the event history. So this raises the question, what if I have confidential information? What if I have a credit card number or a patient ID or, protected health information or any other sort of confidential or sensitive information. I don't want to necessarily have that in the database for somebody to be able to see. The answer is that you can use what is called a custom data converter in Temporal. Every one of our SDKs has an API for this, and the custom data converter allows you to transform a message as it is leaving the worker. So before it even gets across the wire, before it's even sent to the Temporal service, it is encrypted. The transformation oftentimes is used for encryption. So you can encrypt it using a key of your choice, using whatever cipher you want, and then the data is stored in encrypted form in the temporal database. And when it's retrieved, when the worker needs that information, for example, to be able to reconstruct the state of an application following a crash, it is the worker that decrypts the information. So the temporal service in this case only sees the encrypted information. It would not have access to the key and doesn't even know like in what cipher is used to encrypt it. So there's no possibility of it being decrypted on the server side of things. It all happens on the client side within the application itself. So that's the way that it takes place. And that's a pretty good story for security, I think, having the ability to apply that encryption as you wish.
Hey, thank you. We also have a question from Dan. Will this resume behavior only work if retries for the activity or workflow are configured?
Uh, no, the durable execution, so recovering from a crash, is not dependent on the retry policy. So I'll back up and say in temporal, activities are automatically retried upon failure by default. So for example, if we're going to call the service to get the distance to the customer and the network is down or that service is down, there's something that's happening that is making that unavailable, then it will automatically retry that call. The default policy will be that it'll retry 1 second after the first failure, then 2 seconds, then 4, and it doubles until it reaches the maximum of 100 seconds. This is a customizable policy, so you can change the behavior to suit your needs, and you can do that independently for each execution of each activity. So you have a lot of control there. But the ability to recover from a crash is not dependent on having a retry policy set up. So you could say that we won't retry, and Temporal still has the ability to recover from a crash.
Great. We have one more question, unless anybody else wants to drop one in the chat or the Q&A. It says, from activities in event history, is the entire request and response stored for API call?
For workflow execution request and for activity execution request, what gets stored is the activity type or workflow type, which generally corresponds to the name of the function or method that you're calling, and then the parameters that are passed as input, as well as the result that it produces as output. So that's the information that gets put in there. So something that is internal to your activity, so let's say you have 10 lines of code, the input parameters that are passed to that function, that becomes part of the input. Or part of the event history, the value that it returns. But if you have like a local variable within the activity that is never seen external to the function, that would not be in the event history. So it's the input and the results and the name of the function.
Perfect. Seth is asking how many activities per workflow?
That's a great question. There was a blog recently, maybe in the past month or 6 weeks or so, that goes into some detail about how many activities you should have, how granular your activities should be. There's no one right answer. So I'd recommend reading that blog because it gives some great advice. But in general, you're trying to balance two different concerns. One, you want to keep your event history relatively small because that'll give you better performance. And Temporal provides some limits on the event history. Like you'll start getting warnings if your event history becomes too large. And at some point, the execution will get terminated because this could jeopardize all the other workflow executions that are running. So as a safeguard against that, it establishes some limits. So it's important to keep under those limits. So the balance is, on one hand, you want to keep your event history small, and on the other hand, you want to keep performance very good. So every time that you have an activity execution, it's going to result in at least 3 events going into the history: activity, tasks, scheduled, meaning that the task was put into the queue, activity task started, meaning that the worker has accepted the task, and activity task completed or failed or timed out. You'll have some event that denotes how the activity execution concluded. So there's always going to be three events. So if you had, 1,000 events, there are 1,000 activities as part of your workflow, then you would have 3,000 events that take place there, and potentially more than that. Um, so you want good performance and you want to avoid doing unnecessary network calls, but you also want some granularity. So to give an example, let's say that you had an activity that was going to, well, going back to this example where we're determining the distance to the customer's address and charging the customer's payment, if we put both of those things in the same activity, we could do that. Temporal would allow it, but the problem would be the failure of an activity is all or nothing. Like the activity either fails or it completes. There's no sort of partial failure. So if we did the call to get the distance to the customer's address and that succeeded, and then within the same activity we call to charge the customer's payment and that failed, then the entire activity would be re-executed. And so we'd wind up duplicating that call to get the customer address. So to avoid that unnecessary duplication, it's a good idea to make things more granular. But again, it's weighing performance versus how you want your application to be. I highly recommend that blog.
We can put that blog in the follow-up email,
Yeah,
Tom, so we can
perfect.
link to it. Are there common programming challenges that you see pop up when migrating to temporal workflows from a typical system?
Yeah, it requires a different way of thinking about the problem. I tell people and I've taught a lot of people how to use Temporal, created some of the training classes and have taught them and introduced Temporal to a lot of people. And I would say that Temporal is a paradigm shift, really. It's kind of like if you start out learning C language, as I did. That was one of my first programming languages. And then at some point, I learned Java, which is an object-oriented language. It required me to think about problems differently. And I'd say that's true of Temporal. So on one hand, you can sort of brute force just take your existing application and sort of make it adhere to the temporal APIs, and that's not particularly difficult. Most of your heavy lifting, most of the real work that your application does is going to be inside activities. So if you think about your typical application for order processing, you're going to reserve an item in inventory, you're going to charge the customer's credit card, you're going to send a confirmation email, you're going to notify the warehouse that they need to ship the item. You're going to have some series of tasks. Well, the orchestration of those tasks, the sequencing of them, that's in the workflow, and that tends to be pretty simple. Workflows themselves don't tend to have a lot of heavy logic in them. The things that actually do all the work are the activities. That's where you're making the calls to a service or querying a database. That's where you are sending emails or writing to files. That's where you're doing I/O and things like that. And so you can typically just take those functions and just, okay, now it's an activity. Like the way varies by SDK, but in Go, for example, an activity is just a Go function. There's nothing special about it. There's no naming convention. There's no decorator or annotation that you need to put on the function. There's no special handling of it. It's just a function that you register with a worker and then reference from your workflow. Again, different SDKs vary in how they do it, but it's typically not a huge challenge to port applications from another system to Temporal. And I'd recommend looking into how you can do it incrementally. So if you have a system that's made up of a bunch of different components, it could be that you could move one of them to Temporal and then over time move the other ones to Temporal. And often you'll get the most benefit if you begin with the one that gives you the most trouble. If you identify the thing that's the most unreliable, move that to Temporal, then you get the most return on your investment because you're going to make that unreliable thing reliable.
Great. And so another question. So if a worker crashes midway during running an activity, there's nothing else we need to do to have the workflow resumed on a different worker.
That's right. Yeah. So if the worker crashes, regardless of where the worker is within the overall execution, if it crashes, it will be automatically, the task will get automatically rescheduled and it'll get picked up by a different worker. But let me explain that there's really sort of two cases here. If you just have one worker running and that worker crashes, then at this point you have zero workers running. And you can't make any progress if you have zero workers running because workers are the things that run your workflow and activity code. So there needs to be at least one worker running for any progress to happen. This is why I mentioned on one of the slides that it's common to run multiple workers. Even though you only need to have one, it's common to run multiple. So if you had 100 workers running, for example, or even just two, if one worker crashes, the other one will take over for it automatically. There'll be some degradation in performance because you've lost a little bit of capacity, but as soon as you bring up another worker or, set up a new machine to replace the failed one, then they'll just pick up. And also, I want to mention that the way that Temporal works, it's a beautiful design in terms of workers are the things that accept the tasks. So in a lot of distributed systems, Apache Hadoop works this way, for example. It is the master or the main system that assigns tasks to worker nodes. But in Temporal, it's the other way around. It's the workers that pull tasks from the Temporal service. And what that means is the workers won't ever get backlogged because they don't accept tasks that they don't have the capacity to work on. And if you have a backlog because you're seeing a lot of demand, a bunch of tasks are queuing up, and you'll see there's metrics that Temporal provides that'll show you the latency. So if you see that there's high latency among the workers, which is often a clue you don't have enough workers, then you can set up another machine, run a bunch more workers, and that will start to drain this backlog that's queued up in the Temporal service. So you can understand like when you're reaching a problem with throughput, and you can identify it and you can solve it by adding more workers.
Great. And then another question, does history replay call external services from activities, those that are already completed?
No, so it is history replay will selectively execute an activity or not based on what the event history shows. So in the example that I gave before, where it was the get distance function that's calling this microservice, then, and so you could imagine in the code, let me just bring up my notepad over here, type some fake code here. Okay, so I'll increase the font size here. Okay, so this is a made up sort of pseudocode that approximates what it would look like in 4 or 5 different languages. But let's say that we're going to assign a value. This is inside the workflow. We're going to assign the value uh, or the variable called distance. We're going to assign that based on the result returned by the get distance function. So here's how we would call that activity. We'd say workflow.execute activity. We'd pass in a reference to the activity function, and then we'd pass in whatever input is there. Again, the actual syntax of this will vary based on the language that you're using, but this is generally what it looks like. So what'll happen is when the worker, after a crash, when it is going through the code, it's running the code in the workflow, and it's safe to do that because there's no side effects. It's not going to do anything bad. So if it's like totaling up, total price equal sum pizza order, that code is safe to run. It ran it first, during the first execution, but that code is safe to run because like it's deterministic. It has no side effects. But when we get down here and we're calling this function get distance, which is calling a microservice, and that's the reason we have it as an activity, what happens is the worker looks at that and says, oh, instead of just calling a regular function, this is an activity. So let me look in the history and see whether it indicates that get distance was called at this point with this customer address, and if so, whether it completed or not. So if it completed that because the value is stored in the event history, it will then, instead of executing that function again, it's just going to assign the value based on the value that was in the event history. On the other hand, if the event history doesn't indicate that this activity had completed during the previous execution, it will run this. So it'll execute it because it hadn't done it before. Hopefully that answers the question.
Great, thank you. We have a couple more in about a couple more minutes. So we have another question. Is there a way to rerun a workflow that failed?
Yeah. You just you just rerun it. I mean, that's all there is to it. You just rerun it. I will mention that there is configurable in Temporal a couple of different things. One's called a workflow ID conflict policy, something like that anyway. And then workflow ID, there's some other policy. There's two policies. They basically govern this guarantee that Temporal provides. Every workflow execution has a unique ID associated with it, and it's up to you what that ID is going to be. You assign it. It is typically something that has some business meaning to you. So if you're doing order processing, the workflow ID might include the order number or the customer number or something like that. Typically, it might be the order number. This prevents you from having two workflows trying to process the same order at the same time. So by default, the policy is configured that you can only have one workflow with a given ID running at a given point in time. You can make this more restrictive to say, not only do we want to prevent more than one workflow with a given ID running at a given point in time, but if one ran in the past, we also want to prevent a new one from running. So you can configure that, but by default, you can only have one workflow with a given workflow ID at a given time.
Great. Then another workflows will change over time as business changes. Is there a best practice to deal with changes at a workflow design level?
Yes, great question. So in Temporal, when I was talking about how Temporal implements durable execution, it uses this technique called history replay. In the very beginning, when I was talking about another way that you could do it, turns out not to be a very good way. That's by taking snapshots of memory. And one of the problems with taking snapshots of memory is it is based on the code that is running. And so if you make a change to your code, that invalidates the memory snapshot. And so that's bad news because you want to be able to evolve your code. Well, with Temporal, you can evolve your code. However, you have to do so carefully because the workflow execution needs to be deterministic. So if you were to add an activity in the middle, let's say the example that I showed before, I'll just go back there. So let's say that we add right after call service to get distance to address, we added some other activity there. Maybe it would get a credit score for the person ordering a pizza, whatever. If we added an activity right there to the middle, this would break determinism for our workflow because if the thing crashed, then it would look at the event history and it wouldn't see that that activity was there. Like the code and the event history no longer match. And that would be a problem. You would wind up with a non-deterministic error. And this is something that people encounter with Temporal often because they don't understand what I've explained here with history replay. Now you do, so you can avoid this problem. But you can use a strategy called versioning that allows you to avoid that. So you can safely evolve your code. You can add activities, you can remove activities, you can change activities. The trick is you need to do it in a safe way. There's at least three different strategies for versioning in Temporal. We have a training course on it, and it's available for Go, Java, TypeScript, Python, and soon to be other languages. And so we have a training course that explains it in great detail. But the gist of it is it allows you to safely evolve your code. And one way, the most common technique is called patching. And it lets you put in a conditional statement inside your workflow. So you can say, if this is version 1 of the workflow, we're going to do these things. If it's version 2 of the workflow, we're going to do these other things. So that old workflow executions will follow the original code path, but new ones started after the change are going to follow a different path. And it allows you to have those things running side by side. Again, highly recommend reading up on versioning. It's a really important technique for Temporal, and learning about it early on will save you a lot of trouble down the road. And we have a training course on it.
Great. Well, thank you, Tom. Thank you, everyone, for joining and for asking your questions. I'm sorry we didn't get to all of them, but I did post the link to our community Slack in our channel or to our community Slack in the chat. So please go there, and then we will be sending out additional resources with the recording and the deck soon. Thank you very much, and I hope you have a great rest of your week.
Thank you.